Unit 2, Day 10. Piecewise functions continued. This is Mr. McGough again. Today we're going to go over a few more examples of piecewise functions. So in number 1, we have a function g of x that's defined over two portions of the domain. For the values where x is less than or equal to -3, we're going to use the first piece, and the second portion of the function applies for x greater than 2. So here we see that there is a restricted domain where there is a gap where g of x is not defined between x greater than -3 and less than or equal to +2. So let's start with the first piece where x is less than or equal to -3. So we're going to have x and g of x. For x equals -3, g of x is 5 plus 3 times -3. 3 times -3 is -9, plus 5 is -4. And now we need another value where x is less than -3. So let's just use -5. 5 plus 3 times -5, which is -15, equals -10. Let's take a look at the second portion of the graph. For x greater than 2. For x equals 2, g of x would be -2 times 2, which is -4, minus 2, which is -6. Another value greater than 2, to be able to draw our line, let's just throw down 5. We'll have -2 times 5 minus 2. -2 times 5 is -10. Sorry about that. Minus 2 is -12. Now we have everything we need to be able to graph. We are going to want to change our scale again, so we'll use a scale of 2 to 1. Two, 4, 6, 8. 2, 4, 6, 8. Same thing on the negative side. We'll have g of x and x. When x equals -3, first off, it's less than or equal to -3, so this will be a solid circle. When x equals -3, halfway between -2 and -4, y will equal -4. When x equals -5, 2, 4, 6, so between -4 and -6 is -5, and y will be -10. -2, 4, 6, 8, 10. There is no definition or no output for the function between -3 and +2. So we're going to go ahead and leave a gap in the graph. And then when x equals +2, g of x equals -6. So -2, 4, 6. Here we're drawing an open circle because x domain for does not include the value of x equals 2. It's only 2.00000, however many zeros, 1 and bigger. So just slightly bigger than 2. And then for x equals 5, 2, 4, 5, we'll go down, -2, 4, 6, 8, 10, 12. And this portion of the graph applies for all values, x greater than 2. So we'll draw our arrowhead. Our next example. Here, x is defined for a piece of the graph strictly less than 3, and a second definition for x greater than or equal to 3. So this will include the entire domain. There will just be a point of discontinuity, perhaps, at x is exactly equal to 3. So x and f of x, we're going to draw our t-chart. We'll do it first for x less than 3. So we'll put 3 for our x. We'll have negative 1/2 times 3 plus 1. Negative 1/2 times 3 is negative 3/2, or negative 1.5. Plus 1 is negative 1/2. We need another number less than 3. How about a nice round number like 0? So I'll put in 0 for x. Negative 1/2 times 0 is 0, plus 1 is 1. Second portion of the graph, x greater than or equal to 3. Again, we'll check at our boundary when x equals 3. F of x equals 3 minus 2, which is 1. So we'll see that the value is not the exact same. So there will be a jump in the graph at that point at x equals 3. And then we'll take another value greater than 3, let's say 5. 5 minus 2 equals 3. Makes sense. This is a linear function with a slope of 1. And if it included 0, then it would have a y-intercept at negative 2. So let's take a look at graphing this. So first off, for x strictly less than 3, that will be an open circle at x equals 3 and y equals negative 1/2. So 1, 2, 3 for x. I'm using a 1-to-1 scale, and negative 1/2 for y. When x equals 0, y equals 1. Not exactly right. Slipped a little bit when I drew my slope of negative 1/2. But we can always fix it. Close enough. For x greater than or equal to 3, this will be a closed circle at the point x equals 3 and y equals positive 1. And it will go upward at a slope of 1, so when x equals 5, y equals 3. We'll draw our arrowheads to show that the graph continues after those points. Next two examples. On your printout, hopefully you can see the problems, that they didn't get hidden by the graph. I had to actually use the Word document and fix it. So if you don't see, these are the functions we're using. So here we have three parts: x greater than 4, less than or equal to negative 3, and then between the two. Normally we would actually list these in order from left to right as you go across the domain. So let's graph them in order as we go from left to right. So for x less than or equal to negative 3, we're going to start at our boundary condition, negative 3. We're going to put in negative 3 for x. So it's 2 times the absolute value of negative 3 plus 1. Negative 3 plus 1 is negative 2. Absolute value of negative 2 is positive 2. Times 2 is 4. Now, we have to check to see if within this portion of our graph, the graph is going to turn, because this is an absolute value. Remember, those are V-shaped if the vertex is included within it. So our vertex for this will actually be at the point negative 1, because the absolute value of negative 1 plus 1 is 0. So at 0, this is positive 1. At 1, this is positive 2, so it continues to increase. At negative 2 plus 1 is negative 1, but the absolute value is negative 1, or of negative 1 is positive 1. So this turn point for the absolute value is outside of less than or equal to negative 3, so we don't need to worry about that. So we'll just plug in one more point, less than -3. Let's say -5. 2 times the absolute value of -5 plus 1. -5 plus 1 is -4. Absolute value is +4 times 2 is 8. Second portion, we have -3 less than x less than or equal to +4. For all that, it's a constant. So between those points, we're just going to have 8. And then for x greater than 4, let's go ahead and graph this one, or draw out our t-chart for this. For x greater than 4, it'll be x minus 1. Now let's go ahead and graph. We'll start off with this easy 8. So for x equals -3, 1, 2, 3, we'll go up 1, 2, 3, 4, 5, 6, 7, 8. At that point, it's an open circle on this portion of our domain. And then over to x equals 4, 1, 2, 3, 4. It's also +8, and this time it's a closed circle. Second portion, for x less than or equal to -3. At -3, f of x is +4. At -5, 1, 2, 3, 4, 5, f of x is +8. And then it continues upward with that slope of 2. Well, actually it's downward as you go negative numbers, and the vertex would be down here at x equals -1, and then it would start turning the other way. But that's not part of the domain we're graphing. And then for x greater than 4, at x equals 4, f of x would equal 3. So we leave an open circle there. For x equals 5, f of x is +4, and again, etc., with a positive slope of 1. Again, vertical line test, if you take a look, at any point on the graph, a vertical line will only hit one output value for each input value of x. So it is a function. Number 4. This time we see gaps. Between -5 and -3, there is no definition. And between 3 and 4, f of x has no definition. So for x between -5, 1, 2, 3, 4, 5, and -7, the value is evaluated to be -2. This includes the endpoints. Oops, off. 1, 2, 3, 4, 5, 1, 2. 1, 2, 3, 4, 5, 6, 7, 1, 2. That's one piece. Between x equals -3, 1, 2, 3, 0. It includes that point. 3. When x equals 3, f of x equals 0. Also includes that endpoint. And then for x equals 4, 1, 2, 3, 4, all the way out to x less than or equal to 8. 1, 2, 3, 4, 5, 6, 7, 8. Our third piece. Sorry, I'd started and made an error. So I'm backing up. Number 5. So here we have a piecewise function with 1, 2, 3 pieces. We're going to write it as y equals, and then we're going to define our domain chunks first. So there's a chunk where 0 is less than or equal to x is strictly less than 1. The next portion, 1 is less than or equal to x is strictly less than 2. And our last portion, our last piece, 2 less than or equal to x strictly less than 3. Now let's take a look at what our values are across these different portions of the domain. So for x greater than or equal to 0, but strictly less than 1, y is 1. Similarly, for x greater than or equal to 1 and less than 2, y is 2. And for the last portion, y is 3. So those are our 3 portions of our piecewise function. Next, piecewise function for this graph. Let's take a look at the right side first. So the right side of the function is defined for x strictly greater than 0. What is the function? Well, our intercept is at 0. We'll recall that this is a linear function, so it's of the form mx plus b. So 0 is our b, our y-intercept. And then we need our slope. Well, we can use our slope formula, or we could take a look at the graph and count. So on this graph, for every 1 x we go to the right, we go up 1, 2, 3. So our slope is rise over run, or 3x plus 0. So we will write, this is again listed as y. Sorry about that. For 0 less than x, we have 3x. We don't need to write the plus 0. For the other portion of our graph, where x is less than or equal to 0, or 0 is greater than or equal to x, whichever way you like it, we're going to go ahead and say that our function, our intercept, is at the point -5. So mx plus b, since it's linear. -5 is our intercept. And then our slope will take 2 points. We're over here at 1, 2, 3, -10. And then we go right 1, up 2, right 1. So our slope is 2 over 1 times x. So for x less than or equal to 0, we have the function 2x minus 5. Last couple of questions. Postal service. Here we can only have packages greater than size 0. Nobody has negative weight. Nobody attaches helium balloons to their package and tries to put it on the scale. We'll note that the cost is up to 5 pounds depending on the weight in ounces. As a reminder, 1 pound equals 16 ounces. So for less than 8 ounces but greater than 0, $13.65 or $13.65, etc. So we're going to go ahead and graph this. First off, do we need the entire y-axis to be defined? Well, no, because this is actually, the cost starts at a little over $13. So what we can do is we can draw one of these little squiggles, and we'll say that this portion of the graph starts at 13. Now we need to go up to at least 28. 1, 2, 3, 4, 5, 6, 7, 8. Let's see, 8 times 2 is 16. 16 plus 13 is 29. So we can use a 2-to-1 scale. So 15, 17, 19, etc., 21, 23, 25, 27, 29. You can use another scale if you prefer. That is cost in dollars. And this is weight, or W, in ounces. And again, we have to take a look at our scale. This goes all the way up to 80. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 spots. It looks like all of the breakpoints are at values divisible by 8 ounces, or 1/2 of a pound. So we will call this 8 ounces, 16 ounces, 24, etc., 32, 40, 48, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 80 ounces. Right between the two would be about 60. So there's our graph. Now let's go ahead and plot. At 8, it's $13.65, somewhere around in here. So between 0 and 8 ounces, inclusive of 8, exclusive of 0, that's our graph. For the next portion, $17.85. Between 8 and 32. Then the next portion, up to 48, it's $21.05. Here's 21. $21.05 is just slightly more than that. Out to 48. Etc. So, what is the cost to send a parcel weighing 2 pounds and 9 ounces? Well, 2 pounds is 32 ounces, plus 9 more ounces is 41 ounces. So all we have to do is look back up at our table and see where 41 falls on our list of domains, domain chunks, little steps, and that's $21.05. Thanks.